So what was I saying? Yeah, so these are improper integrals, specifically type 1 improper integrals because it has infinity limits. And then someone also said partial fractions. Well, if you look at the first one, it is possible that it might be a partial fraction. Remember that partial fraction is a method of integrating. So we might need to use partial fractions, we might not. Usually you want to avoid partial fractions if there's an easier method of integrating. So let's just see, let's take a look at part A to see what we can do here. So let me switch to Paint. All right, so here's part A. Before I rewrite it using the notation needed for improper integrals, let's discuss how we can integrate this. So one person said partial fractions, which is fair because the denominator, you can factor it into two parentheses. But is there another way we can factor this? You can use sub. Maybe. How can we use u sub for this? U equals w to the 4th plus 1. Let's see. Let me write that down. So if you let u equal to w to the 4th plus 1, then du is 4x to the 3rd dx. Yeah, you could definitely do that. So 4x to the 3rd is fine because we do have x to the 3rd inside our integral. So this is definitely valid. There's a rule where you have the integral of negative infinity and positive infinity. Okay, I'm not gonna be able to check that out right now, but I'll definitely look at it when the class ends. So I would say that u substitution is easier than partial fraction. So let's do it this way. So if we were to continue with the u sub, first we have to break apart the improper integral because we can't have two infinities. So you can go from negative infinity to positive infinity. And then you can go from, sorry, not positive infinity, negative infinity to 0, and then 0 to positive infinity. All right. So this is 6w cubed, w to the 4th plus 1. Okay, so this is what we have so far when we break it apart. Let's try integrating it now. So let's just do that on the side. We are trying to integrate 6w squared, 6w cubed, or x w to the 4th plus 1 squared. So this is what we're trying to integrate. We already said our u substitution is going to be this stuff over here. So let's try to put everything in terms of u. First thing I'm going to factor out is the 6. Okay, so we have, focusing on the denominator, this is parentheses u squared, right? And then we have a 1 on top. We also have a w cubed dw, which we can rewrite as du over 4, right? So if you just go here, you divide by 4, then these go away. And this is what you're left with as your integral in terms of u. Okay? All right, so now it's 1 over u squared, which we should be able to integrate. So this is u to the -2 du. All right, so to integrate, we have to add 1 to the exponent and then divide by the new exponent. So it will be u to the -1 divided by -1. But then we can just put the negative here. So this is our result. And then let's just put what u was back in. So -6 over 4, w to the 4th plus 1 to the -1st power. Okay, and then let me just rewrite this in simplest form because we're gonna have to evaluate it later. So it's probably better to do that. So -6 over 4 times w to the 4th plus 1 to the +1 power, okay? So this is our result. So we are going to have to evaluate this result by going back to our integral here. So this is -6 over 4, w to the 4 plus 1. We're going to evaluate this from -infinity to 0, and then plus -6 over 4, w to the 4th plus 1, evaluated from 0 to infinity. Okay. So hopefully you guys are okay with that. Make sure you know how to integrate using u sub. And then at this step, you just need to evaluate the limits. Okay, so recall how to evaluate stuff when they go to infinity. So let's do that now. Okay, so remember that the top limit goes first, right? So we're gonna plug in 0 first into w. So if we have -6 over 4 times w to the 4th plus 1, and then we plug in 0, what do we get? Let me see. I think that's just -6 over 4, right? Yeah. Okay, so that's the top limit plugged in. Now we're gonna subtract, and now we're gonna plug in the bottom limit. So recall that when you plug infinity, it's technically a limit, right? So what happens as a limit of w? Sorry, what happens when w approaches -infinity? Yeah, it goes to 0, right? Because the denominator gets bigger. So that goes to 0. And now let's do the other one. So we have the top limit of infinity. We're going to plug that in. That should give you 0 again, right? Because it's to the 4th power. So that's 0. Then now we're going to do the bottom limit. So when you plug in 0, you get -6 over 4. Okay, so here's our numbers. And then when you add it all together, do you get something? Is that just 0? I think that's just 0, right? All right, yeah, so this is 0. So what was the question? Determine whether it converges or diverges. If it converges, state what value converges. All right, so how can we answer the question in a complete sentence? Yeah, converges to 0. I mean, that's not complete. I mean, doesn't matter. You don't need to have perfect English here, but you can just say converges to 0. Yeah. So this converges to 0. Let me write that. All right, so that's part A for number 5 done. Let's move on to part B. Okay, so here we have part B. Let's read the directions. So the directions say to use the comparison test to determine whether the integral converges or diverges. Okay. So again, we said this is an improper integral, right? But even though it's an improper integral, they specified a particular method that we have to do this. So we have to follow that method using the comparison test. So does anyone have a suggestion as to what we can compare this integral to? Remove the 5 from the denominator. All right, let's do that. So we have the integral from sine of x minus 4 x squared. Okay, so there's the 5 removed, but then the question is, what inequality should we put? Less than. Let's see. Let's think about that, see if that's right. So the original integral has a plus 5 in the denominator, which means it has the bigger denominator, and bigger denominator does mean it's smaller overall. So yeah, this is less than. Okay, but sine of x minus 4 over x squared, we still don't know whether that converges or diverges. So we have to keep going. We have to keep comparing to something else. Take out the negative 4, okay. Hopefully that's also going to be a less than, because, you know, if you use a different inequality sign, then it kind of messes up the comparison test. So hopefully it keeps the inequality sign. All right, so here's the minus 4 removed. Is it still less than? Is this right? Yeah, so minus 4 from the numerator is less than. Okay, that's fine. So sine of x over x squared, do we know anything about that integral? It converges. How do you know? The p-value of x squared is 2. So be careful. You can only use the p-value when you have it in the form of it doesn't even have a name, but you want it in the form of 1 over x to some power. Yeah, they're just calling the exponent in the denominator the p-value, because in the general form is 1 over x to some power p. But yeah, let's keep thinking. So we're not allowed to conclude that it converges just because there's a square in the denominator, because it's not in the form 1 over x to some power. So let's see, what else can we do? So someone says, shouldn't it be oscillating and therefore divergent? So trig functions like sine and cosine are oscillating, but this is not just trig function. It's sine over x squared. So that we don't know what that does. You took out the sine and it'll be less than or equal to. You took out the sine. So what did you replace sine with? Like, did you just write 1 instead of sine? Okay. Yeah, I mean, that's in the form of p-value, so maybe that might work. But then the question is, what's the inequality sign? You said less than? Okay. Why can you put a less than sign here? Okay, less than or equal to. Yeah, why can you put that? Sorry, this is a 2 here. I don't remember the reasoning. Yeah, okay, so sine can be less than or equal to 1. Sine is, yeah, so, I mean, you two are sort of right, but you just like, the word you guys are missing is range. So the range of sine, which is the y value of sine, only goes between -1 and 1. So it doesn't matter what x value you put into sine, it's always going to be between -1 and 1. So it's never going to be as great as 1. Or that's why the inequality works, because the numerator here can be between -1 and 1. So that's why this inequality works, because here we just have 1. So yeah, that's the reasoning. And then, well, this is good because we reached the form of this integral here. So when you have it in that form, remember the rule we said where if you look at the exponent, that dictates whether it converges or diverges. So here the exponent here is 2. And then when it's 2, does it converge or diverge? It converges. All right, hopefully that means we can reach a conclusion, right? So if this converges, and then we followed the inequality back, can we conclude that our original integral also converges? Yes, very good. So anything less than convergent is also convergent, right? So we can just say the integral converges. So yeah, one comment I want to make is that if we did all this work and then at the very end, we, so let's say this is the last step. Let's say at the last step, we arrived at a divergent integral, then this would be inconclusive because being less than divergent doesn't really tell you anything, okay? All right, could you repeat the reason how you arrived to 1 over x squared? Yeah, I'll repeat that. So we were trying to compare, what was it? Sine of x and 1. So you have sine of x and 1. And then if you were to write an inequality sign between these two functions, you put a less than or equal to because the range of sine only goes from -1 to 1. So it's always going to be less than or equal to 1, which is why we are able to put this inequality sign here. Does that clear it up, Devin? Okay.
Professor, I actually had a similar question. I was going through the homework and I didn't know how to solve. Is it okay if we go over that?
Yeah, but since we started this, I'm going to ask you to wait until we finish number 5 and number 6 on the review sheet. So after we finish
All right.
everything today.
All right.
Okay. So someone has a question that says, can an inconclusive be an answer, or would that mean you did something wrong? That's a very good question. So if you get inconclusive, there is a chance that you did nothing wrong. It's just, you got inconclusive. But what it can also mean is that there is another path to the comparison test. So, for example, you see these integrals we chose to compare it to. You don't have to choose these three. So if you choose a different path, it could give you inconclusive, but then there could be another path that doesn't give you inconclusive. So when you get inconclusive, it doesn't necessarily mean you did it wrong, but it could mean that there is a different path for you to take. Hopefully that makes sense. Yeah, let me see if I'm able to come up with an example here. So this was convergent. One over x squared. Yeah, no, I can't really think of an example off the top of my head, but I mean, as long as you show your work for these things, like when I make a question, like I might have inconclusive or convergent or divergent, and you might get an answer that doesn't match mine. But if I see your work and I see that like all the integrals you compare it to are reasonable and you have the right inequality sign, then I'll give you the credit, like as long as you know how to use the comparison test. So yeah, don't worry too much about that. All right, let's go to the next question. Question 6. Question 4. I think question 4 we did it like at the very beginning of last lecture. All right, so here's question 6. Let's read the directions. So determine whether the following series converges or diverges. If it converges, state what value it converges to. All right, so part A. Here we have a series. So take a look at this series for part A. When you look at it, does anything come to your mind? Not in the right form. Why? Is there a specific form you're looking for? Yeah. Okay, what form would that be? Smithing like AR to the end. Oh, so the geometric thing, right? Yeah, so we learned about this special form called the geometric series, which says if you have the index start at 0 and you have A times R to the n, infinite geometric series, this is one of the special forms. Or if you want to use the index shift, you can start at 1 instead. But then this would be a to the r to the n minus 1. So this is the form of an infinite geometric series. You're saying that we can get that in the form. I mean, it doesn't look like a geometric series. Not to me, at least. But what about this series tells you that it can be put into the form of a geometric series? Because that's really the main idea here. If you're able to identify that, then you know what you need to do. So this thing right here. Okay, so my question is, this green part that I boxed, what is a characteristic about this expression that tells you it might be a geometric series? The exponents? Yes, yeah. So notice that n, which is the index, is in the exponent. So that's really the clue here. So whenever you see an n somewhere in the exponent, do try to see if you can get it into the form of a geometric series. So let's see if we can do that here. How do we start? Anyone want to tell me how we can start this? Start by splitting the 5 to the 2 plus n into 5 to the n times 5 to the 2. Okay, I'll do that. So n equals 0 to infinity. This is 5 to the n times 5 to the 2. All right. What else can we do? Split it into 2 series. Okay, could you be more specific? So, oh, I see. Yeah, okay. So, yeah, notice the numerator is basically just 2 things added together. So you can split it into like 2 fractions, sort of. So let me move this. So we have one series, which is 5 to the n times 5 squared over 2 to the 2n plus another series, which is 6 over 2 to the 2n. All right. Yep. Now what? Doesn't look like a geometric series yet. I have an idea. We can rewrite 5 squared as 25. Let's do that. 25 times 5 to the n. Okay. How do we split the 2 to the 2n? Mm. 4 to the n? How'd you get 4 to the n? Yes, very good. So recall that when you have a power to a power, that's when you multiply the exponents. So 2 to the power of 2n is the same as 2 squared, all of that to the nth power. Okay. And then someone said take out the 6. So let's do that. So this is 6 summation of 1 over 2 squared to the power of n. Okay, this is looking good so far. It looks somewhat closer to a geometric series. So regarding the first series, 2 squared is 4, right? So on the denominator, we just have 4 to the n. But then when you have a 5 to the n on top and a 4 to the n on the bottom, you can write it together. So then this would be 25 5 over 4 to the n. Yes, very good. Okay, and then the next one. So on the bottom, we have a 4 to the n. And then on top, we just have a 1, right? But recall that 1 to any power is 1. So you can still write it as 1 to the n over 4 to the n, right? Because 1 times 1 times 1 is still 1. So this is a convenient way of rewriting it. And then if you look at what we have here, we can write this as 1 over 4, all of that to the n. So let me just do that. Okay, great. So yeah, I think these are geometric series now. Right. So in the first series, 25 is your A, 5 over 4 is your R. And then in the second series, well, the way we have it here, your A is 1 and your R is 1 over 4. But some of you might opt to just like leave the 6 inside the summation. In that case, your A would be 6, but it doesn't really matter. You'll get the same answer anyways. I'm actually going to opt to bring the 6 back inside because I think I just like it better. So 6, 1 over 4 to the n. Okay, so these are in the form of a geometric series now. Keep in mind that our index was 0, right? So because our index was 0, we have to get the exponents to be just n. And the index was 1, then you have to get the exponents to be n minus 1. Okay, so just keep that in mind. So this is fine. Let's try to find the values of these series. So who remembers the formula for the sum of an infinite geometric series? A over 1 minus R. Yeah. A of 1 divided by, yeah, same thing. Right. So A is the first term. You can denote as A of 1. That's some people do that. But it's the first term divided by 1 minus the common ratio. Make sure you guys are careful with like the way you put into the calculator, because if you just put like A and then you calculate, you press divide, and then you do 1, and then you do minus, and then you do R, this is not going to give you the right answer if you just like press it in that sequence in a calculator, because your calculator is going to do this first, and then it's going to divide by the R. But yeah, so this is the formula for the sum of the series. So let's write sum. So right before you even use the formula, because if it has a sum, that implies that it's convergent. You have to make sure it's convergent first. So Devin, right, that's the rule for deciding whether a geometric series is convergent. So the common ratio has to be less than 1. So looking at these two series here, do they both converge? Right, so the first one fails, right? Because the first one has a common ratio of 5/4. So the first series is not going to converge. Uh, yeah, let me write out the terms of this series just so we can sort of see why it doesn't converge. So this series, when n is 0, you're going to get 25, right? That's the first term, plus, and then when n is 1, you're going to get 25 times 5/4 plus 25 times 5/4 squared plus, and so on and so on. So you can see that the terms of this series are actually getting bigger as you go on. So if you're adding bigger numbers, then your sum is obviously not going to be finite. So that's why there's that rule where your common ratio has to be less than 1. So this diverges. Okay. All right. So because this diverges, what should we do? What should we do now? We can find the sum for the other series, right? So what should we conclude for this question? Or if we can. Divergent. I mean, are you sure? Don't you want to um, find the sum of this series as well? We didn't do that yet. Does it matter? Haha, good question. I don't know. Can someone answer that? If one is divergent, then the whole thing is divergent. Yes, very good. So yeah, it doesn't really matter. So we can just ignore this one, even though it's convergent. So who cares? Because if you're adding a finite number to infinity, then it's still infinity. So divergent plus convergent is still divergent. So yeah, we're done here. We can say that part A is divergent. Okay. So what's the takeaway here? Just be sure just be mindful of questions that look like they might be able to be put into a form of a geometric series. That's the whole takeaway. So look at the exponent. If there's an n there, then you can probably get into the form and then use the appropriate sum formulas. Okay. All right. Let's move on to part B. Here's part B. So same directions. We want to figure out whether this is convergent or divergent. So we have arctan, right? Arctan of n. Who has any ideas here?
I'm not sure if this is right, but can we do limits?
I mean, it depends. If you're using like a particular method that wants you to take a limit, then yeah, sure. But what are you thinking?
I don't know what the method is called, but I remember like taking the limit of the function. So tan arctan of n.
Limit as n goes to infinity.
Oh yeah.
Okay. Well, all right. I guess we can do that. So limit as n goes to infinity of arctan. I mean, what does this give you though?
Pi over 2.
Pi over 2. I think that's right. Let me try to remember what the graph of arctan looked like. So tan looks like this. So if you flip it, it should look like this. Yeah, yeah. So this is pi over 2. Yeah, okay, so the limit's pi over 2. That's fine. But like, does that help us in any way? The test you're referring to, does anyone know like what the test is called that she's referring to?
I remember it said if the limit does not equal to 0, then it diverges.
Okay. Oh, yeah, okay, yeah. There is a name for that test. Who remembers the name for that test? Yes, very good. It's called a divergence test. Yeah, it's pretty self-explanatory, actually. So this is not equal to 0. So therefore, we can conclude this diverges by the divergence test. Who would have guessed this is what this test was called? Anyways, so yeah, that's the divergence test. Let me pull up the definition for divergence test just so we see what it said. Yeah, that's all you have to do for a divergence test. Let's see, I believe it was 8.1 because that's sequence. Oh no, 8.1 is sequences. I need to go to series. Divergence. Yes, okay. All right, here is the definition for the divergence test. I pulled from the PowerPoint. So it says if you have a series and you take the limit of the expression as n goes infinity, and if that does not give you 0, then the series will diverge. Which, if you think about it, is pretty easy, right? All you have to do is take the limit, which usually doesn't take that long. So, yeah. Is this test intuitively obvious to you guys? Like, if the limit doesn't go to 0, does that seem intuitive that it would diverge? Yeah. Why can't it go to 1? Why would limit of 1 be divergent? Okay, I can answer that. So if your limit was going to 1, that means every term in your series, as you go further and further in, will approach 1, right? So let's say I have this series, like 1.5, and then 1.25, 1.125, 1.0, 625, and so on and so on. So these are terms which approach 1, right? But if it's a series, you have to add them all together. And then as you go further and further in, what you're going to have is, something close to 1 plus 1 plus 1 plus 1, and so on and so on. So you can see why this would reach infinity. So if the terms in your series don't go to 0, then the sum is not going to be small enough. So that's why it will diverge. All right, but anyways, you don't really need to know the details of that. So I guess the takeaway here is that whenever you're faced with a series that looks kind of weird, like you're not sure which method to use, do try the divergence test because that might work. Okay, yeah, I think that's good. Let me just see if anyone said any comments. Some people said the integral test. Oh, interesting. Could we have done the integral test here? Well, recall that before you even do the integral test, you have to check whether it's eligible for the integral test. And there was 3 conditions. So do you guys remember what those 3 conditions were? Yeah, continuous function. Let me just put the graph of arctan back just so we have it for reference. So it looks like this, and then looks like this. And then here is pi over 2. And then on the bottom, it's negative pi over 2. So it is continuous. Does it satisfy the other 2 conditions? Right, positive and decreasing. So here if we were to write this as an integral, the bottom limit is 5 and the top limit is infinity. So 5 would be like over here. And then, so everything that's inside the boundaries, so from 5 to infinities, it is positive, right? Because it's above the x-axis, but it's not decreasing because it's actually going up. So this is not eligible for the integral test. So you cannot use the integral test here, unfortunately. Yeah, that sucks. Also, another reason why we shouldn't use it is because I don't think we know what the integral of arctan is. So that's another reason. All right. Yeah, I think was that the last question? Yes, that was the last question. All right, so I just want to take a moment just to talk about the test in general, like how the questions are going to work. So if you look on this review sheet, let me go back to the review sheet. Starting from the beginning. So each question is based off of one of the sections on the syllabus. So if you look at the syllabus, we did 6 sections after exam 1. So that's why there's 6 questions here. So I just want to take a moment just to label each question with what section they're on, okay? Just so you can, be prepared for all the possibilities of a certain question, okay? So number 1, this is the integral test. So that means on your exam, there's going to be a question that wants you to do the integral test. So be prepared on how to do that. It will be the same format. So it will allow you to just skip the prerequisite conditions. So you don't have to check for like continuous and decreasing and stuff. But do make sure you know like all the methods of integration. Mostly the basic ones, so like U substitution. I'm probably not going to give you integration by parts because like that's a little bit too tedious. So yeah, that's one of the questions. Yeah, same as last time. So you can submit it through email. I'll have the instructions on how to submit it like on top of the exam. Number 2, so this one says evaluate the integral, but if you guys remember for number 2, this was partial fractions, right? So that means there's going to be a question on the exam that wants you to do partial fractions. And then you'll need to know how to identify like which question that is and then how it looks like, as well as the process. So make sure you know how to tell whether it needs to do long division first, and then make sure you know how to solve for like A, B, and C and all those constants in the numerator, okay? Question 3, this is a sequence. So we did a section on sequences. So there will be a question on sequences, and then you'll need to know how to decide if sequences converge or diverge. Number 4 is approximating integrals. Yeah, that one's fine. So there's 3 ways that we learned. There's the midpoint rule, trapezoidal rule, and Simpson's rule. Each of those have their own formula, so just know how to use those formulas for this particular section. Number 5, we did that today. This was improper integrals, okay? So just remember how to solve improper integrals, as well as a comparison test. And then there will be a question regarding series. So do recall all the methods we use to solve for series. So know how to tell if a question is a geometric series, as well as keeping the divergence test in the back of your mind, okay? In fact, I would suggest whenever you're faced with a series, just try the divergence test right away, because if that works, then that question was really easy. Okay, so that's 6 questions. I'll probably have an extra credit question in there just so I can keep it consistent with the first exam. And yeah, that's pretty much all I wanted to say. So any questions you guys have? Only 6 questions? Yeah. Basically 1 question per section. Yeah. All right, so there was one student who asked me if they wanted to look at a homework question, but seeing as how we just finished everything that's in our agenda, I'm gonna stop it here. So if you have no further questions, you're free to leave, and I'll see you on Thursday for the exam, okay? Anyone that stays, you guys can stay if you have any further questions, but for now, our class is over, so you guys are free to leave. Yep, good night, everyone. All right, the student who had a question regarding the homework, you want to go over it now?
Yes, Professor.
All right.
It's from 8.3.
Okay, let me pull it up. What question on 8.3?
It was number 8.
8, okay. Number 8. Screen. So here's number 8. So this one says use the comparison test. All right. Did you try this yet?
Yeah, I did. And
Okay.
I also, first of all, before we go ahead and start the comparison test, if I were if you just told us to determine whether this series is convergent or divergent, right? Mm-hmm. I would use the limit formula thing where I can compare use my series as a function and just determine the limit to determine its convergence or divergence, right?
Oh, so you mean use the divergence test?
Yeah.
Yeah, I mean, we could try that. Yeah, so if you do n squared 4n to the third minus 1. So if you take the limit and n goes to infinity, what do you get?
Divergent.
No, you would get 0 because the degree in the denominator is bigger.
Okay.
So if you want to see why that is 0, so you can divide every term by n to the third. So this would be 1 over n, and this would be 4, and this would be 1 over n to the third. Do you see what I did?